Look at page 25, question 36. Okay, page 25, question 36. Okay, I'm going according to the questions that I sent to you last week. All right, so the question is telling you you have a potential meter, 100 centimeter potential meter wire QT that is connected in series with a 2-volt cell. Another circuit consisting of 2-volt cell in series with resistors of resistances 4 ohm and 6 ohm is set up alongside the potential meter. Connections PQ and RS are then made so that the potential difference across the 4 ohm resistor is balanced against the PD across the length L of the potential meter wire. Both cells have negligible internal resistance. Okay, so here the question already kind of mentioned to you that your galvanometer reading is already 0 because they say it's balanced across length L already. Okay, so this one you know is already balanced. It's already equals to 0. So one of the main thing that you learned last week was that I mentioned to you whenever you reach balance length, the PD across this top portion here will be the same as the PD across this bottom portion here. Okay, so to write it in words for you, this one I can just say PD. Let me just write it. PDQS is the same as PDPR. Okay, so at balance length, at balance point, okay, at balance point, PDQS is the same as PDPR. Okay, so when you look at this potential meter here, the potential meter is basically this top part here. Right, this is your potential meter circuit. This is potential meter circuit. Okay, and then this one is the circuit whose PD you're trying to measure. And this one is the circuit whose PD is being measured. Okay, so you have the top circuit and the bottom circuit. So one thing I should mention to you also is that the top circuit has its own current flow, like this. This one current at the top, and then the bottom circuit also has its own current flow. This one, it will look like this. This one is I bottom. So one of the main thing I mentioned to you is that the current at the top circuit and the bottom circuit will never cross at balance point. They maintain in their own respective circuit. So right now, you want to find out what is the balance length L. Okay, one way to go about it is to find out what is the PD VPR first. Then you can equate it to PD VQS and use the relation V is proportional to L. Okay, so here, I want to find out what is VPR first. Remember last week I told you the potential divider equation V out is equals to R1 over R1 plus R2 times V in, provided that the same current flows through all the resistances. So you can actually apply it over here in this line. Because you see 4 ohm and 6 ohm, they have the same current flowing through. This one is the entire circuit. I can actually apply potential divider equation here. So I can say that VPR is the same as 4 over 4 plus 6 times with V in, which is 2 volts. Eventually, I will get the answer as 0.4 times 2, 0.8 volts. Okay, so this length here corresponding to VQS would have a PD of 0.8 volts. Okay, so that's what you understood from here. So therefore, VQS is equals to 0.8 volts. Okay, so this is the first thing you can do. All right, then the next thing you can do here is this. If you are talking about the full length of your, sorry, maybe I use a different color. If you're talking about the full length of your potential meter wire, okay, this full length here, if you were to apply Kirchhoff's second law for this circuit alone, this one being 2 volts would mean that the full length of the wire here is going to be 2 volts too. Okay, so the full length of the wire corresponds to 100 centimeter. Okay, I know that this entire potentiometer wire has a full length of 100 centimeter, and when I apply Kirchhoff's second law for the top circuit, I know there is 2 volts. So I can then use this relation that I had last time. V is proportional to L, V2 over V1 is L2 over L1. So say right now I use it for, maybe I write it better properly here for you. I can say that VQS over LQS is this over VQT over length LT. This is the ratio I can get. So VQS is 0.8, VQT is 2.0, LQS is what I want to find, LQT is to 100 centimeter. Okay, so eventually I find out that LKS is 0.8 divided by 2 times 100, giving me 40 centimeter. Okay, so this one answer is B. Right, it makes use of quite a number of things you've learned before this. Right, okay, so this is question page 25, question 36. Then after that I move on to 69. All right, I just show you the working. All right. Okay, now 2 cells are investigated using a potentiometer at balance point. 2 cells are being investigated using a potentiometer. At balance point, cell X gives a reading of 44. Cell Y gives a reading of 70 centimeter. Which of this statement here is actually not correct? Okay, so if we read the statements one by one, a potentiometer balance point results in 0 current through the galvanometer, which is this one. This one we know of for fact is one of the main characteristics of the potentiometer. Your aim is to always make your galvanometer reading 0. At that point, it's called your balance point. So this statement is considered to be correct. Okay. Now then after that, second statement. At balance point, the current through resistor R in both circuits is the same. This one actually would be correct. Okay, it's kind of related to what I mentioned to you just now. At balance point, no current will flow, right, through the galvanometer. In my current case, if I look at both circuits, there is actually current flowing, but not at the bottom circuit, but at the top circuit. The current flows like this. Okay, so at balance point, there is no current that is going to flow to the bottom circuit. It's just going to flow, for the top circuit, the current will just be confined within the top circuit itself. Okay, so here at balance point, the current through resistor in both circuits is the same. You look at your case here. Okay, you look at the situation that has been described here. This one, if you just compare the green colored loop itself, they are exactly identical. Okay, they are exactly identical. You see, they are having exactly the same EMF. They're having exactly the same resistor. They're having the same potentiometer wire. So for all manners and purposes, your current will be exactly the same. Okay, so this statement is correct. All right, because at balance point, current won't go anywhere. It will just continue flowing within the top circuit. The top circuit itself is exactly identical. All right. Okay, then after that, if you look at the answer choice C, answer choice C. The EMF of cell X is larger than that of cell Y. EMF of cell X is larger than that of cell Y. Okay, so the thing here was that you always remember that whatever EMF that you have here, wait, sorry, your EMF of X will be equal to the PD at balance point. Then this one, the EMF of Y will be equal to the EMF, the PD across the balance length. Okay, this one is what you understood once you have achieved balance point. So the two things here is that when you wanted to find the PD across here, you have to use this relation. V is proportional to L. If your balance length is larger, your V is going to be larger. But in your case here, your V is actually equal to the EMF being measured. Okay, wait up. Let me write this. Your V at the balance length is actually equal to the EMF being measured. So here, V is proportional to L. Length increase, V increase, the EMF increase. All right. So you look at this one. This one is 70 centimeter. This one is 44 centimeter. So obviously, EMF of Y will be more than EMF of X. So this one is actually going to be incorrect because it's saying that cell X EMF is larger than that of cell Y. It should be cell Y EMF is larger than X. This one is wrong. Okay, so the statement that's not correct is this one. Okay, the value of EMF of each of the cell X and Y is less than 6. Okay, that is correct. This is correct. Okay, one thing I never did mention to you guys is this. Let me just erase this one. One thing I never did mention in your notes was this. Remember, one of the characteristics of your potentiometer circuit is that you always need to have your driving cell. Okay, you need to have a driving cell in your potentiometer. Okay, so the thing that I didn't really mention was that the EMF of driving cell must be larger than PD or EMF being measured. Okay, it has to be larger. If let's just say this one, for example, I tell you my cell has an EMF of 12 volts, but my driving cell EMF is just 6 volts. So how are you going to get 12 volts across this length? You see, like what you see right now, if I have a 6 volt EMF here, and then I have resistance R here, and have the resistance of the potentiometer wire here, by Kirchhoff's first law, you know that this one itself will never be 6 volts. It will be less than 6 volts. Okay, and at balance point, you know that whatever PD or EMF you have here must be the same as the PD across the given length of the wire. So if right now you are having a case where your EMF is 12 volts, but this one here, the total length is just for the total length of the wire, you're getting less than 6 volts. How are you going to get 12 volts from this length? It's just not possible, right? So that's why we tell you EMF of your driving cell must be larger than the PD or EMF being measured, so that this entire length here will have an EMF large enough to account for the EMF or PD being measured. Okay, so let's just say again, I use by this example. If say my EMF is actually 12 volts right now, with this 6 volts EMF, this entire length will be less than 6 volts. I cannot get 12 volts out of that. So the only way I can use this potentiometer again is if, say, maybe I go and change this EMF to maybe 30 volts. So there's a chance that this entire length could be more than maybe 15 volts. So in this case, this EMF of 12 volts can be represented as part of the length here. Okay, so that's what I meant. All right, so just make sure that the EMF of your driving cell is more than the EMF or PD that's being measured. So this one is correct. Okay. Yeah, the value of EMF of each cells X and Y is less than 6 volts. That is correct. Okay, it must be less than the EMF of the driving cell. Okay, must be less than EMF of driving cell. Okay. So this one is correct. So the only answer wrong is answer C. Okay, so that one is all right. Then I move on to the next one. Okay, page 114. Okay, this one, let me fill off everything. Okay, now you have a power supply and a solar cell that are compared using a potentiometer circuit as shown. The potentiometer wire PQ is 100 centimeter long and has a resistance of 5 ohm. The power supply has an EMF of 2 volts and the solar cell has the EMF of 5 millivolts. What resistance R must be used so that the galvanometer reads 0 when PS is equals to 40 centimeter? Okay. So based on what is being mentioned here, there are some things that you can start to deduce. Your solar cell has EMF of 5 millivolts. So this one is 5 millivolts. And your galvanometer is really reading 0 when the length is 40 centimeter. So you know that at balance point right now, your galvanometer is already at balance point, at balance length, okay, whichever. When your galvanometer is reading 0, you're already at balance point. This length 40 centimeter here would already represent a PD of 5 millivolts. This one is your resistance wire of your potentiometer. So 5 millivolts is for length PS at balance point. Okay. Then after that, what the question actually wants you to do now is to find out what is this resistance R. So you have to do something like backtracking a little. All right. So what you can do is, say, for example, right now, you can find out certain things from here. Let me just see where is it. What resistance R must be used so that the galvanometer reading reaches 0. Okay, so this one here, you understood it as having a length of 100 centimeter. Okay, but what is the PD across this? So you can use V equals to, V is proportional to L. So V PQ over V PS is equals to L PQ over L PS. So VPQ over 5 millivolts. LPQ is 100 centimeter over 40 centimeter. I don't really need to bother changing the centimeter to meter because the units will cancel off. And likewise, since this is millivolt, I also don't want to bother changing it because whatever unit that I have here will follow the unit of this. Okay, so that's the reason why I didn't really bother changing the units. So eventually you get VPQ times 5 as 12.5 millivolts. So this one here is going to be 12.5 millivolts. Okay, now from here, you can actually start to use your potential divider equation if you wanted to. Right, so what you can do is this, there's actually two ways to go about this. I show you using potential divider first. Using potential divider equation, so balance point current will only flow in this length, across this closed loop that I indicated to you here. So you know for sure you definitely can use potential divider equation here, right? So let me just draw the current I for you. This one is I, this one is also I. So you can use potential divider equation straight. So what you can do is that if I wanted to find out what is the voltage VR here, I can do so. Before I do that, I can actually find out what is this voltage here. Wait on. I can say using Kirchhoff's second law. Kirchhoff's second law tells me that in a closed loop, sum of EMF is equals to sum of PD. So I know that EMF is equals to VPQ plus VR. So EMF is 2 volts, VPQ is 12.5 times 10 power minus 3 plus VR. VR is going to be 2 minus 12.5 times 10 power minus 3. You're going to get 1.9875 volts. Okay, so this one is the voltage across here. Now from here, you can actually use potential divider already. I can say that VR is the same as R over R plus the resistance of PQ. You already have the resistance of PQ as 5 times with V in. So this one will be 1.9875 equals to R over R plus 5 times with V in 2. So you just work around it. What you get is R plus 5. Then this one is 2 divided by 1.9875 times R. 2 divided by 1.9875 is this value of R. Then after that, R would be that value minus 1. 5 divide that. You're going to get the answer as 795 ohm. This is one way of doing this. Okay, there's another way to do this also. This one is if you do not like to use potential meter equations. Potential divider equation. Now, this one comes from here. What we can tell you is that you already found out BPQ is 12.5 millivolts for this entire length. Okay, and you already know its resistance as 5 ohms. You can actually find out what is current through the wire itself. So if let's say I use an alternative method, B is IR, I'll just say for wire PQ, make my life easier. For wire PQ, V is equals to IR. This one is 12.5 times 10 power minus 3, I times 5. So I 12.5 times 10 power minus 3 divided by 5. You're going to get 2.5 times 10 power minus 3 ampere. Okay, this one is a A. Then from there, you proceed with step B. Okay, now, just now you already used Kirchhoff's second law to find out the PD across VR. Okay, you can also use back V equals to IR for resistance R now. Okay, for resistance R, or resistor R, right? Sorry. For resistor R, you can say that you're using V equals to IR. Let me use a better color. Okay, you can use back V equals to IR. Your PD is now 1.9875. Your current is now 2.5 times 10 power minus 3 times R. Your R should be giving you the same answer. Okay, you're getting 795 ohms. Okay, so there are two ways to go about it, whichever you like now. Okay, but you see the principles in which they use always rely back on what you've just learned. Okay, so that one is for this. This one is 114, I think. Hey, sorry, 114. Then I go to 125, just to illustrate to you even more examples. Okay, page 125, question 38. 125, question 38. Right, you have a potential meter circuit that is used to determine the unknown electromagnetic force EMF of cell X. In the circuit shown, E is a cell with EMF that is known accurately. QR is a potential meter wire which has movable contact S. Contact S is connected to a galvanometer and to a cell X. What is not a necessary requirement to determine the EMF X from the circuit? They want you to tell us what is not the necessary thing to know when you want to determine the EMF of X. Okay, right. So again, this one kind of relates back to what we kind of learned just now. Let's go through the statements one by one again. All right. The EMF of cell X must be lower than the EMF of cell E. This one is actually correct. This is why I mentioned just now. This EMF must be larger than this because EMF of driving cell must be larger than EMF or PD measured. This one is a necessary requirement. Otherwise, you cannot find out you cannot find the required PD from the given length here. All right, whatever PD or EMF that you measure will always be a fraction of the total PD across the full length. Okay, it's only then you were able to use the concept of potentiometer. All right. Okay, the internal resistance of cell X must be known. This one is actually not required. I mean, what does the internal resistance of cell X tell you? It doesn't tell you anything, right? Because at balance tank, as I mentioned to you, in your current case here, when you're connecting to a EMF, a source of EMF, just a battery, no circuit whatsoever, other than just the battery itself, current will only just flow like this in the top circuit. The bottom part here has no current flow. Okay, maybe I better just highlight it as this. Okay, no current flow. Therefore, effects of internal resistance is ignored. Okay. Internal resistance only becomes a problem when you have current flowing through it, because then it causes you to have voltage loss. So answer B is actually not the necessary requirement. But then we can also do double checking on answer choices C and D. The lengths QS and QR must be determined accurately. Yes, this one is correct because you are relying on V proportional to L, where V2 to V1 is less equal to L2 to L1. You need to determine the lengths accurately. This is necessary requirement. Okay, and then the resistance of wire PQ must be proportional to the length. This one here, okay, I should use a different color. They're saying this one must be proportional. This one is again something you have learned in the notes, where I mentioned to you resistance is proportional to length. It was because of this relation that eventually you got to this relation. So this is also correct. Okay, so answer choice is B. Okay, so that is one part. Then after that, let me just see the next question just to see. Okay, now this one is doesn't look like a potential meter, but it's still based on the concept of potential meter. Just let me explain this to you. Okay, page 16, question 38. Now in the circuit shown, xy is the length L of uniform resistance wire. A potential difference is applied across xy, R1 and R2 are unknown resistance. J is a sliding contact that joins junction R1 and R2 to points xy through lamp S. So J is moved along xy to a point at which the lamp is off. The point is the distance x from x. The potential difference across R1 is V1 and potential difference across R2 is V2. What would thus be the value of the ratio V1 to V2? Okay, now when you look at this one, that may not seem like a potential meter to you, but it actually is kind of like part of a potential meter. Okay, you see, if I imagine that there is a cell here, this one positive, this one negative, because this one I see is positive, this one is negative. All right, this one here is already kind of like your potential meter. All right, and then after that, if I look at the bottom circuit, I can also kind of imagine it as having a circuit connected that looks like this. Okay, notice that this is actually kind of like part of a potential meter circuit, which if you look at your notes, kind of looks like the example in page 12. It kind of looks like this, right? So what you're seeing there is like your potentiometer. If you imagine a little about where is it connected to, it's actually your potentiometer. Okay, and the only difference now is that rather than using a galvanometer to indicate that current is zero, instead they're using a lamp. You see this one, they're using a lamp, not a galvanometer, but the same principle still applies. The only thing about a galvanometer that you want is to show that the current is zero. The lamp will also work just as well. When the lamp is off, current is zero. Okay, so in a way, this one is already telling you you have reached balance point. So same concept applies. So here I can tell you a number of things. In my case here, I can say that at balance point, VR1 is going to be the same as Vx. Then after that, another thing I could also say here is that VR2, wait, I'll use what color? VR2 is going to be the same as the PD across here. Okay, this one is VL minus X now, all right? Okay, so what are the ratio of the values of V1 to V2? Okay, now this one maybe I don't use R1, R2, I just use it straight as V1, V2. I use this as V1 straight. I use this as V2 straight. Okay. So here I know that the length is, okay, maybe I just write this. This one, the length is L minus X. This one, the PD across it is V L minus X. Okay. So at balance point, V1 is the same as Vx for this entire length. V2 will be the same as the PD across L minus X, which is this one. So since I know that V is proportional to L, I can say that V1 to V2 would just be X divided by L minus X. So answer is D. Okay. So this one is for question 6, page 60. Right, so that one is okay. Then I will go through one or two more examples. Okay, maybe this one I can. Okay, 67 is not really your potential meter, but it deals with part of it. Okay, so have a look at page 67. Okay, the diagram shows a battery of EMF 6 volts connected in series with resistor and uniform resistor wire RQ of length 60 centimeter. The resistance of Y of RQ is equal to the resistance of the resistor. Okay, so this one is an important thing to know. The resistance of RQ is equal to the resistance of the resistor. So meaning to say, if this one was R, this one would also be, if this one has resistance of R, this one would also be R. The resistance is the same, okay? So what they're telling you here is that terminal X is connected to fixed point R, which is here to here, and terminal Y is connected to point P, which is from here to here. Okay, a connection that can, P is a connection that may be made at any position along the wire. P is movable. L is the distance between R and P. Okay, which graph shows you the variation with L or the potential difference V across XY? Okay, across XY, what is the variation with L of the PD across via XY? Okay, so the only thing that you really should bother about here is that you know that for the resistance wire, B is proportional to L. Okay, so your length L can vary from 0 to the full length. Okay, your length can vary from 0 to some other value. So they want you to find out what is the PD across that length. Okay, now one thing you can do here is this. One thing you need to see here is that since V is proportional to L, if you were to plot a graph of V versus L, you should get a straight line graph that passes through the origin. Okay, that is what you should know. Because if L is equals to 0, meaning to say it's going all the way to here, you have 0 PD. But then after that, when you go all the way over here, you have the full PD. So what you're interested in is the PD across the full length. Okay, this one say is the full length. Okay, what will be the PD across the full length? So this one you need to use Kirchhoff's second law. Right, so one important thing that they mentioned to you was that resistance of RQ is equal to resistance of the resistor. So what this would in turn mean for you is that if your EMF is 6 volts, under Kirchhoff's second law, you know that your PD will be split between the wire as well as the resistor, so that the PD adds up to become 6. But because you have equal resistance for both cases, this tells you that this one will be 3 volt, this one will be 3 volt. Okay, so this one is fact number 1. Okay, B is okay. B versus L will be is straight line through origin. Okay, number 2 here is that PD across full length is 3 volts because total PD is split equally. Total PD is split equally between wire and resistor. Okay, so your answer will obviously be B. Okay, so answer is B. This is the correct one. Okay, so that one is one thing here. Okay, then there were some other things. Okay, let me just ask you guys this. For the rest of the potential meter questions, were you guys okay with it? Do I still need to continue explaining some of the things? Any? So it's okay lah, all right. Okay, so maybe I go and do something related. Okay, let me see the one with potential meter. Okay, right. Oh, there was some other stuff here. Let me just see. Let me find out the potential meter and the short circuit one. There was a question on that last time. That one is right here. Give me a second. Okay. Okay, so maybe I try to find out a question for you that involves the special potential meter and the short circuit thingy, just so you guys know what I'm talking about. Okay, can you guys have a look at page 74? Potential divider, I don't think I need to explain so much about it because it's pretty straightforward. The issue is usually potential meter. Can you guys just have a look at page 74? We'll try and do a structure question here. All right. This one is November 28, 10P23. Okay. Right. So November 28, 10P23. Okay. Okay, now state Kirchhoff's first law. This one, some occurrence into a junction is equal to some occurrence out of the same junction. This one, no issues with this. This is something that everyone should know. Okay, now a potential meter is connected to a battery of EMF 9.6 volt and negligible internal resistance as shown. The maximum resistance of the potential meter is 800 ohms. A resistor R of resistance, wait, let me just adjust the screen a little. Okay, the maximum resistance of the potential meter is 800 ohm. A resistor R of resistance 400 ohm is connected between the slider and NX of the potential meter. Okay, so this is your 400 ohm connected between the slider and NX of the potential meter. Okay, now state the potential difference across resistor R when the slider is positioned at NX and at NY. Okay, so this one is that little special potential meter that I was talking to you about just now earlier in the lesson. It is not the potential meter that you learned in the last lesson. This is kind of, this potential meter here is kind of like a variable resistor. All right. Okay, so what happens when you were, if you were to put your slider at NX? Say right now your slider is this. You go and change it to this end here. Okay, so remember just now I mentioned to you, if you go and put it at this end, is akin to you connecting to before the resistor. Okay, if you were to connect it to say Y, is akin to you connecting to right after the resistor. But if let's say you're connecting it somewhere in the middle, like this, is akin to you splitting up the total resistance. Okay, so this is what potential meter actually is. In your case now, the special potential meter. Okay, so now we go to the part where they talk about nx of your potential meter. Okay, nx of your potential meter refers to this case. So if you want to draw an equivalent circuit of what you have here, it looks like this. Okay, let me just erase all certain things. It looks like what you have here. All right. So you have that same circuit, but because you're connecting it at nx, sorry, let me just adjust my pen. Okay, because you're connecting to nx of your potential meter, is the same effect as connecting to right before the resistor itself. Okay, so this is your equivalent circuit right now. Now, once you look at this circuit, you will be able to see that if I were to let current run out of the battery from here to here, it will eventually reach a junction here. But then once it reaches this junction, there are two possible paths for your current to flow. Either it flows here, or either it flows here. Okay, but you see between these two paths, one of the paths actually does not have resistance. The green colored path with the 400 ohm inside actually has resistance inside. But the blue colored path, which is just the wire, which we assume has no resistance, actually has zero resistance. So that part there is your short circuit. Okay, so current at this point, at this junction here, it will not flow to the bottom portion because it has another better place to flow through, the path with zero resistance, the short circuit path. So your current will actually just flow through here instead. Continue like this before going back to your circuit, before going back to your battery. So now the question is asking you the potential difference across resistor R when the slider is positioned at NX of potential meter. The potential difference across resistor R is the 400 ohm resistor. Okay, so since you already identified that this part here has no current through it, there's no current through R, therefore there won't be any PD through R. So the potential difference is just zero. That's the understanding to this question. Okay. Now, if you look at the other part where they ask you about NY of your potential meter, NY of your potential meter, if you're connecting it across NY of your potential meter, which is over here, is akin to you connecting to right after the resistor. So your equivalent circuit looks like this. Okay. This is now your new circuit at NY. Okay. So now they want you again to find out what is the PD across these 400 ohm resistor. There's actually no calculation that needs to be done here. It's a simple matter of just applying Kirchhoff's second law. When you look at this circuit here, yes, you can say current I flows. Once it reaches this junction, there are two possible paths. This path and this path both have resistance, so there's no short circuit here. Current will actually just split out to I1 to I2 here, and then join back here to become I. Okay, so there's no short circuit here to consider. But then after that, when you want to find out the PD specifically across this part, there's no calculation. This one, if you understand Kirchhoff's second law, you will be able to see that this one is actually just going to be 9.6 volts. Same like this one. This one will also be 9.6 volts. Why? Because Kirchhoff's second law tells you that sum of EMF is equals to sum of PD in a closed loop, in any closed loop. So there's actually two loops here that you can consider. I'll highlight it for you. Your first loop is this one, the one in orange. You have only one EMF, you have only one PD. Across the 800 ohm, obviously it's going to be 9.6 volts. Your second loop will be the blue colored loop that I highlight here. Okay, Again, you have only one EMF, you have only one PD. So your PD here must be 9.6 volt. So without any calculation, you should know that this one is just 9.6 volt. Just like that. Okay. So this one is a question that combines to you your short circuit knowledge and your potential meter knowledge of the special kind. All right. So this one is okay. All right. Then after that, you go to the next one. Okay. This one is also testing you on your potential meter, but the more advanced understanding of your potential meter. Okay, let's read through the question. They tell you to calculate the potential difference across resistor R when the slider is positioned halfway between X and Y. Okay, so if your potential meter, the special potential meter, is positioned halfway between X and Y, I mentioned to you before, it has the effect of splitting your resistor in half, resistance in half, so that this one is 400 ohm, this one is 400 ohm. Okay, so this one is talking about this case. You will split your resistance in half. Okay, so your equivalent circuit looks like this. Let me just zoom out a little so that you can see everything. Okay, so your equivalent circuit now looks like the diagram that I showed here at the bottom. Okay, 9.6 volt, 400 ohm, 400 ohm, 400 ohm. This is the resistor R whose PD you want to find. Okay, now this one, you want to find the PD, you can use potential divider equation. But remember what I mentioned to you before, if you try to use potential divider equation to find the PD across a resistor, please make sure that the current through the resistances are the same. So like in my case here, this is not as simple as you saying, I want to find the PD across here, so I say that the PD is 400 divided by 400 plus 400 times with 9.6. This is not correct because you see the current here is not the same. This one is I, it reaches here is I, but then here it splits out to become I1. This one is splits out to become I2 before joining back here to become I. So clearly you see your resistances do not have the same current. So I cannot use this one straight. Okay. What I did mention to you was that you could try to simplify the circuit so that the same current flows through all the resistances. So you try to simplify your circuit, it now becomes this. This is now your new circuit. What you try to do is you simplify the parallel resistance. The equivalent resistance is just 200 ohm. Now this one in turn relates back to what you learned in DC circuit, the parallel resistance part that I mentioned last week also. So under page 6 of your notes, I mentioned to you that in your parallel, if you have n number of resistors whose resistance is the same, they are connected in parallel, your resistance, your total resistance is just the submultiple of the resistance. If let's say you have 5 resistors of same resistance, you take the resistance divided by 5. Likewise, if you have 2 resistors of the same resistance, you take the resistance divided by 2. That is what you are doing here. Okay, this one you're actually making your life easier because you see that there are 2 resistors of the same resistance. The equivalent resistance is just 400 divided by 2. That's why you get 200 ohm here. Okay, so this one again relates to what you just learned in the resistances in parallel. Now from here, your current will be the same. You see, current now is same throughout your resistances. So from here, you can actually make your life easier already. Your V is actually just supposed to be 200 divided by 200 plus 400 times with 9.6. That's why you get the answer as 3.2. Okay. Yeah, this one, the resistance, I already found it here. right? But if you know the shortcut, you can just straight away say it's 200. Okay, there's a C mark here. This one means that when you see that the marking scheme has a C mark allocated to it, it just means that your working must show that you know that particular information, you know that particular thing. But it doesn't need to be specifically shown in your answer. Your workings must imply that you know it. So let's just say you had not shown this one, but then you just show this one. So this 200 here implies that you know this already. So you will still get your other C mark. Okay. But if let's just say you in doubt, you're not sure, just write everything down if time permits. Okay.